Welcome to lecture 22. In this lecture and the next lecture, we will talk about two very simple graph traversal algorithms. So for this lecture, we will talk about the breadth search algorithm, and usually we use BFS as a shorthand notation for this searching method. As for the next lecture, we will talk about another one called depth search, whose acronym here is DFS. Okay, before that, let us review what is a graph and the graph representation. So first of all, a graph is a structure that consists of vertices and edges. And there are two main types of graphs. It could be undirected, where there are no directions on the edges, and there could be directed graphs, so that each edge there is a certain direction. Now, for the undirected graph, we can store the graph by using the adjacency list as follows. So we will use a vertex V. So for each vertex V, we will use a list to store all the neighbors of V. So here in this graph, we have the vertices 1, 2, 3, 4, 5. So we will have a list of one for vertex 1, a list for the vertex 2, and so on. Now here we see that 1 has 2 and 5 as its neighbor. So in that case, the linked list of 1 will contain 2 and 5. And for this vertex 3, it will have 2, 5, and 4 as its neighbors. So in that case, the linked list for vertex 3 will contain 2, 5, and 4. So here, this is representing just the neighbor relationship, so it doesn't matter how the order of these neighbors are present in the list. So it could be in any order. Now similarly, the adjacency list can also work for representing the directed graph. So the same here. Each vertex V, we will have a list storing all the neighbors. So here, for this vertex 3, it has a directed edge pointing to 2. So in that case, 3 will have a neighbor of 2. So we are going to store the out neighbor of the vertex. So for this vertex 5, it has an outgoing arrow pointing to 3 and then another one pointing to 4. So 5 will have two neighbors, 3 and 4. Okay. Now, the adjacency list representation has the following behavior. So first of all, the space for this one is very good. So it takes order V plus E space, where V represents the vertex set, E represents the edge set. So the space is actually linear. So in order to represent the graph with V vertices, you still need V space, and E edges, you just need at least E space. So it is quite good, linear space. And then it is excellent when E is very small. And also using adjacency list, if we want to list out all the neighbors of a certain vertex, it is very efficient. We just access the corresponding list. However, if we want to check directly whether two particular vertices they are neighbors, then it is very slow. In the worst case, we need to go through the whole list in order to confirm that a certain vertex is not a neighbor of the other one. So it could be very slow. And then we can modify the representation so that the adjacency list can also be used to represent weighted graph. So sometimes there may be weights associated to the edge. Let's say this is going to be a map, and then the edge represents the length of the road, or there could be also weights on the vertices, which represents, let's say, the population of a certain city. So in that case, we can modify easily the representation so that we can represent a weighted graph using adjacency list. Now, another very common representation method is called the adjacency matrix. So for this one, we are using a matrix to indicate whether two vertices they are connected or not. So here, 1 is connected to 2 and 1 is connected to 5. So in that case, in the matrix, the entry for 1, 2, the entry for 1, 5 is 1. So it represents that these two vertices are the neighbors of 1. And that 0 represents that it is not connected. So we are going to use a matrix as the representation. So similarly, for directed graph, we are going to use the matrix to represent whether, let's say, each row, okay, the vertex on the row has an out arrow, out edge to the vertices of the corresponding column. So for instance, 2 has a pointer that points to 1. So 2, 1 is 1. 2 also points at 3, so you have 2, 3 to be 1. And that's it for 2. So in that case, we can use this adjacency matrix to immediately represent whether there is a direct edge from U to V. Okay. So here, when we use adjacency matrix, the space is order of V squared. Yeah, because we need V by V matrix. Okay. So V square entries, order V square space. And it is really bad when E is small. So when E is small, so let's say the whole graph has just one edge, but still, we will still need to use V square space. Okay. And also, enumerating all the neighbors of a vertex is very slow. Yeah, because we need to look at each entry corresponding to a certain vertex in order to check whether it is a neighbor or not. But on the other hand, if we just focus on checking whether two particular vertices, whether they are neighbors or not, then it is fast because it is a matrix, it gives us the answer immediately. And also, this representation can also represent a weighted graph, no matter it is edge weighted or vertex weighted. Okay, now we have introduced the two very or the most common representation for a graph. We are now ready to talk about the breadth search algorithm. So for breadth search, it is the method that based on the following idea. So it will first of all, it will try to find all the vertices that is reachable from a particular vertex S, which we call the source vertex. Okay. So the idea of breadth search is to explore the graph in rounds such that at round K, we discover the vertices whose distance from S is exactly K. So how do we do so? So this is the algorithm. So first of all, we'll mark S to be a vertex that is already, okay, so this is discovered in round 0. So at the beginning, we start from S, so it is already discovered. Now we are going to enumerate, okay, to run in rounds. So for round K is equal to 1, 2, 3, and so on and so forth. We will look at each vertex that is discovered in round K minus 1. So we will look at the vertices that are discovered in the previous round. When we look at each vertex like this, we will mark the vertex as visited. So we are now checking this vertex, and then this vertex is visited, and we will not check it anymore in the future. When we check a certain vertex, what we are going to do, we will look at every neighbor of this vertex. Now, if a certain neighbor is not visited and also not discovered, then in that case, this is going to be a vertex that is unseen before. So this vertex V will be labeled as discovered in this round, in round K. So this is very simple. Round 0, we have S. Round 1, we will look at this S and look at all the neighbors of S. In round 2, we will look at all the nodes that is discovered in round 1, and then we will look at all the neighbors of these nodes, and so on and so forth. So as time goes by, more and more vertices will be discovered and also visited. So we will stop when there are no more vertices discovered in the previous round. So if there is a round that there are no more vertices discovered, we will end this for loop. Okay, this is a very simple example demonstrating how BFS works. Okay, so let's start with the vertex S. So we're using this notation. A dotted line here represents that the vertex is being discovered. And then if the vertex is marked solid here, then it means that we are now checking this vertex and it is now visited. It will not be seen anymore in the future. Okay, so we start from S, round 0. And then at round 0, so we are now going to move on to round 1. So in round 1, we look at the vertices that are discovered at round 0. So we mark a 0 here. So we look at all the neighbors of it. So these are the vertices that are discovered in round 1. And after that, we will pick, so this is done for S. And then after that, we look at the vertices that is discovered in round 1. Let's say we pick this one. And then we look at the neighbors of it. So if a neighbor is newly seen, then we will discover it. But no, for this particular vertex, there are no new neighbors that is going to be seen, that is unseen before. Because this neighbor, the previous neighbor here is already visited, and this neighbor is already discovered. So this one is done. Okay. After that, we are checking this one. So when we check this one, we discover a new neighbor. So in this new neighbor, we are marking this as discovered in round 2. And after that, we have done with this, we have done with this. After that, we look at this one. So we are going to visit this one and then make the neighbor of this one discovered in round 2, this round. So after that, we have seen all the nodes that are discovered in round 1. So this is done for round. This checking the nodes discovered in round 1 is done. Okay. And we proceed to check the nodes that is discovered in round 2. So the 2 nodes discovered in round 2 will be seen one by one. So when we see this, there is no new node being discovered. Okay, so we are done with this one. And after that, we are going to move on to this one. When we move on to this one, then we have newly discovered a vertex here. So this is vertex 3 here, this one. So we are done with round for checking the nodes that is discovered in round 2. And next, we look at this node. We found this one. And after that, we found this one. And then there are no more nodes that is discovered. So we are now end after we have done this one. So we are done when there are no new node discovered in this round. And this one is the end. And then actually, we have also marked the directions of some edges of this graph. Okay, in particular, where we have a directed arrow when we have a node discovering another one. So we have this as a directed arrow here. S discover R, S discover W, S discover X. But on the other hand, we do not have any arrow for this W and X. It is because W and X, they are not one discovering the other. Okay, so in that case, in the end, we will obtain this case, and then we can easily see that S will be the root node, and this is actually a certain tree, and this tree represents the relationship of which one discovering which one in the BFS algorithm, and so we call this a BFS tree of S, rooted at S. Okay. Now the correctness of BFS is very easy, so we can prove by induction that if a vertex has distance k from S, so distance k means that the shortest path from S to the vertex V is equal to k edges, then it must have some neighbor such that the distance of S to this neighbor is k minus 1. Okay, a distance k node will have a neighbor whose distance from S is k minus 1. So this is correct, okay? And then after that, we will see that V must be discovered in round k because by induction, all the nodes that is of distance k minus 1 will be discovered previously. So in that case, S will be a neighbor of it. So in that case, V must be discovered in round k. So this can be easily shown by using induction. A node will be discovered in round k if and only if the distance from S to the node is exactly k. Yeah, this is easily seen. Okay. Okay, now to keep track on the discovered and visited status of each vertex, so when we run this BFS algorithm, we need to check whether a node is visited, whether a node is discovered, or whether they are not both. Okay, so in that case, we can use a simple array of length order of v. Okay, so we could have an array of size order v. Okay, to remember what is the current status of a vertex. Okay, and then because when we run the algorithm, we need to keep track on what are the vertices that is discovered in a certain round. So we can actually use a linked list to do so. Okay, we can use a list for representing those vertices that is discovered in round 0, and then another list for round 1, another list for round 2, and so on and so forth. Now, after that, it is just running the algorithm. And then we see that each vertex will be discovered at most once, and also each edge is processed at most 2 times when we are looking for the case for the undirected graph. So in that case, the total running time is linear, order of v plus e time. So the time we spent on the vertex is order v. The time that we spent on the edge is order e in total, so v plus e time. But actually, we can do something a little bit smarter in the implementation. So instead of using a separate list for the discovered vertices in each round, we can actually use a common queue. So let's call it big Q. Okay. So whenever the queue is not empty, we will pick a vertex from the front of queue to visit. The earlier the vertex is in the queue, the earlier that it is being discovered. Okay. So in that case, when we visit a vertex picked from the front of queue, then we will do the same thing as before. We will discover the neighbors of it. And now, when the vertex is newly discovered, then we will simply insert it to the end of the queue. So in that case, if we look at the queue, then all the vertices in round 0 will be before all the vertices of round 1 will be before all the vertices of round 2 added to the queue. And then we are going to process the vertices in this order. So we are going to process the vertices according to rounds. Okay. So actually, when we apply this method, there is actually no improvements in time or space for the whole algorithm. But then the implementation is much simpler because we do not need to maintain rounds, and we do not need to maintain a separate list for each round. Okay, now let us look at one application of this method. So the BFS algorithm can be used to find the connected components of a graph. So all the connected components of a graph can be found in linear time as follows. So initially, we mark each of the vertices as undiscovered and unvisited. Okay. Now what we are going to do here is that we are going to check for each vertex u. Okay. One by one. If u is not visited, then we will run BFS with u as the source vertex. So running this will eventually discover u and visit u and so on and so forth, so that all the vertices in the same connected component of u will now be visited after this round. And after that, we will process another vertex such that we process it whenever it is not visited. In that case, when we process this the next time, we will be selecting some vertex from an unvisited connected component, and after that we are going to visit all the vertices in such a connected component, and so on and so forth. So each time that we run BFS, we are actually running this BFS on the vertex in some newly discovered connected component. Okay, so in that case, we can find all the connected components in this method, and then the total time will be proportional to the number of edges for this case, that is for equal to the or proportional to the number of edges of the connected component that we are seeing. So in that case, the total time is still bounded by order of v plus e. Okay. Okay, so that's all for the introduction of this BFS method. Thank you.